Yes, hi, this is George Rakis again, and today I would like to do a problem in longitudinal waves. So what's the problem here? On the upper figure we have a graph of displacement versus the distance that the longitudinal wave is traveling. And actually, let's first take the snapshot at t is equal to 0. So what we have here, these red points, they represent the displacement of the particles, of these 12 particles from 0 to 12. So these represent the displacement, this graph here represents the displacement of the particular particles at the t is equal to 0. So the first question is on the bottom figure to draw the location of these particles at this particular time, at t is equal to 0. So first of all, in longitudinal waves, the particles they travel at the same or the opposite direction that of the propagation of the wave. So that means that in this case the wave, so that means that the wave is traveling in this direction. So that means that also the particles, they are traveling like in, either in this direction or in the opposite direction. So actually they are traveling in a parallel direction with the wave. So that means that at t is equal to 0, at t is equal to 0, this particle here, 0, is at the position of equilibrium. So it's here. At t is equal, particle 1 now, at t is equal to 0, is at the displacement 0.5. This here, from here to here is 1. So, and here is the 0.5. So that means that particle 1 at t is equal to 0 is at 0.5. So, the position of equilibrium, it's here for t, for particle 1. So, it's actually at 0.5. So that means that it's at positive. So that means that it goes to the right of the position of the equilibrium at distance 0.5. So, and since this here, its distance is 1, so that means that here is the 0.5, so particle 1 at t is equal with 0 is here. So particle 2 now, we see that it's at the maximum distance from the position of equilibrium, so that means that here is the position of equilibrium for 2, so that means it's at the maximum distance, which is 1, so that means that particle 2, it will be in this position. Now, particle 3, it's at the half position again in the positive direction. So that means that it will be to the right. So 3, it will be exactly here. 4 is at equilibrium, so it's here. 5. Now 5, it's at distance 0.5 again, but now it's on the negative. So that means that if the 5 at position of equilibrium is here, so it's at 0.5, but actually to the negative. So that means that it's to the left. So that means particle 5 is right here. Now 6, it's on a maximum to the negative. So that means that 6 should be here. 7, it's on half to the negative, like it's 0.5 to the negative. So that means here is at the position of equilibrium, so it should be here. 8 is at the position of equilibrium. 9 now again goes up, so here is the position of equilibrium, so here is where 9 is. 10, it's at the maximum to the positive, so that means that it goes 1 to the right, so it's here. 11, it's again, it's half, 0.5 up, so that means it's to the right, so that means that 11 on equilibrium is here, so at 0, so so that means that it goes, so that means that t is equal to 0 is here. And of course 12, it's at position of equilibrium, so it's here. So now also the question asks to find the areas of compression and rarefaction. So if you can see the figure, the areas of compression, it's right here, and of rarefaction are right here. I mean, and of course this is also a position of rarefaction, and of course this here is a position of compression. So that was part 1 of the problem. So now we know that this wave is traveling with a speed of 2 centimeters per second to the right. So the second question is to draw a displacement graph at t is equal with 1. So what we have to do is we have to move, this graph here at t equal to 0 to the right. So if you do that, we get this graph here, okay? So that should be at t is equal with 1, and why we have to move it 2 centimeters is because it travels with 2 centimeters per second, so times 1 second, so that should be 2 centimeters. So that's why we have to move the one with the red dots to the right 2 centimeters. Finally, the last question is to locate the 12 points again at t is equal with 1. So we have to do this again, of course, in the lower figure. So here we have the green dots, which represents the points at t is equal with 1. So, we see here that point 0, it's at negative 1, so that means 0, negative 1, so the point 0, it should be here. The point 1 is negative 0.5, so that should be here. 2 is at position of equilibrium, so it's here. 3, it's up by half, so it should be here. 4, it's 1 up, so it should be 1 to the right. 5, it's half up, so this is 5, so it should be half, so 5 is here. 6, it's a position of equilibrium. 7, at this point here we have both the green and the red light and the red dot. So for the green dot we have that it's at negative half, so it's here. For 8, it's at the negative 1, so it has to be to the left 1, so it's here. For 9, it's half down, so it has to be half to the left, so it's from here goes here. So 10 is at the position of equilibrium, so it's here. 11 is half up, so it goes from the initial point to half to the right, so it's here. And finally 12, it's at 1 up, so it goes 1 to the right, so it's right here. So thank you for taking the time to view this video, and I hope you find it useful, and bye for now.